So I'm going to go over this worksheet, and if you want to try and do some of it ahead of time or pause the video and do some problems and then check your answers, that'd be great. Objective here is to approximate area under the curve by using left-hand, right-hand, midpoint, and trapezoidal Riemann sums. And we'll start with sort of a practical example. An ant walks back and forth to collect and carry food to its colony. Function v of t equals negative 2t plus 6 models the velocity of the ant measured in feet per minute. So use a right Riemann sum with 5 subintervals to find the displacement of the ant during the time interval 0 is less than or equal to t is less than or equal to 5. Show the rectangles you're using on the graph below. Indicate the sign of the area of each rectangle with little pluses or minus. So here's the ant moving back and forth, moves to the right for a while because her velocity is positive, and then moves back to the left. So basically the ant, maybe has a colony here and some food here, and maybe moved here and then is on her way back, right? Positive velocity and then negative velocity. So 5 subintervals, 0 to 5, pretty clearly we want them to have a width of 1. So I'm going to draw my little lines here to indicate my subintervals. Then it says use a right Riemann sums. Riemann was this German guy who came up with this idea. Right Riemann sum meaning we're using the right side of the subinterval like so. So we use that as our height of each rectangle. The right hand, draw back to the left, like so, like so. So you got to be careful because these ones are under, but then this one's over, okay? So this is all positive area, which means we're moving to the right and our displacement is going to be positive. Then we've got nothing going on here, and we've got negative area and negative area, meaning our displacement is to the left. So basically if we were to find this, each one has a width of 1, and then we're going to multiply by the heights. So this one has a height of 4, this one has a height of 2, this one has a height of 0, this one has a height of negative 2, and this one has a height of negative 4. So that's actually 1 times 6 minus 6, which is 0. So with this approximation, even though from the picture of the graph it looks like she walked farther to the right than the left, with this approximation it actually tells us that she didn't move. Well, she moved, right, but she ended up back where she started, right, because she went 6 this way and then 6 back this way, and so her displacement from the original starting place was 0. But that's partially because we're missing all of this area in here. So we're missing more area in the positive side than we're adding on the negative side. Or rather, we're adding more on the negative side and we're underestimating the positive and overestimating the negative. And so this isn't actually accurate. And we should definitely say 0 feet because this is minutes, and this is feet per minute. So when you multiply minutes times feet per minute, you should get feet. Find the exact displacement of the ant using your knowledge of geometry. Great, so that's a triangle, that's a triangle. This triangle should just be 3 times 6 divided by 2, and this one should be 2 times negative 4 divided by 2. So that should be, let's see, 3 times 6 is something like 18 divided by 2 is 9, minus minus 4. So that should be 5 feet. So her actual displacement was 5 feet, meaning she went to the right 9 feet, and she came back 4 feet. So her displacement was 5 feet, right? And this is all this area here, right, is her positive 9 feet that she moved to the right, and all this area is the 4 feet that she came back. So the error then would be 5 minus 0, or 5 feet. So a ton of error, a ton of error. Way too much error. Okay, let's come back over here. use a left Riemann sum with 10 subintervals to estimate the total distance traveled by the ant during the time interval. So total distance traveled now, everything is positive because we're trying to figure out what was her total distance. So she went to the right, then she went to the left. We want all this to be positive to see what her total distance traveled was. So if we're going from 0 to 5, I want subintervals, 10 subintervals, they should all be basically a width of 1/2. So we're going to get all these little subintervals here, 10 subintervals. Left Riemann sum, meaning we're using the left side for our height. So it should look like this. That one's going to be 0, then this one, that one, that one. So there's plus, 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 0, minus, 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 minus. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rectangles. Okay. However, I guess since we're actually doing total distance, we want these to be positive as well because we want her distance going to the left to be positive as well. So we're going to use those to be positive. So our width was 1/2. Now we need to multiply by heights. So 6 plus, so plugging in 1/2, I guess we should get 5. Yeah, these should come down 1 every 1/2. 6 plus 5 plus 4 plus 3 plus 2 plus 1 plus 0. Then plus 1 for this one, plus 2 plus 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 1/2 times 11, 15, 18, 19, 21. 22, 23, 24, 27, which should be 13.5 feet. Again, that's the time interval, so 0.5 minutes. And these are all her speeds. And these are actually speeds, right? Because we made the velocities positive. So these are speeds in feet per minute. So when you multiply a little time times a little speed, you get a little distance, and adding them all up, you get her total area, her total distance traveled, which is 13.5 feet. Okay, finally for D, it says use a trapezoidal Riemann sum with 10 subintervals to estimate the total distance traveled by the ant during this time interval. Show the trapezoids, indicate the sign of the area of each rectangle. Okay, well, it's not a rectangle, it's a trapezoid. That was dumb. Oh well. So again, they should be width 1/2. And instead of having a rectangle, we're going to have a trapezoid. So you'll notice that a trapezoid on a linear function actually gives you the exact area. Interesting. Makes sense, I guess. So I'm not going to bother to compute all those. We want total distance traveled, so positive, 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 positive. They're all going to be positive. And basically, I can just find the area of this giant triangle instead of doing all the trapezoids. And I already did that on the page before. And I got 9 and -4, but this time I'm going to get a 9 and +4 because I want it all to be positive, and that should give me 13 feet as her total displacement. So this is actually 13 feet, but so is that. So there's no error here. Great, because I found it exactly, and trapezoidal gives me the same, and then the error up here was 1/2 foot. So I'm just thinking about some of these different approximations and how much error they give you. Okay. Now is when we really get into it. So x² + 3 estimate, and this basically means the area. Okay, so this should look familiar from antiderivatives, but this we're going to estimate now the area under f of x, area under the curve for 0 to 5. That's what this means using the right endpoint approximation. So hopefully you're noticing, oh, there is our little height, right, the f of x. Remember the f of x sub I from earlier? And this is the little delta x, the dx, okay? So, and this is our sum, so it sort of looks a little bit familiar. So 5 subintervals, right endpoint, okay? 1, 2, 3, 4, and 5. Right endpoint is going to be there, 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 and there, okay? X squared plus 3, so if I plug in 1, I should get 4. So that should be 1 times 4 plus, if I plug in 2, I should get 4 plus 3, which is 7. Plug in 3, I should get 9 plus 3, which is something like 12. When I plug in 4, 16 plus 3, which is 19. Plug in 5, 25 plus 3, which is 28. So that should just be 4, 7, 11, 23, plus 19 plus 28, which is, let's see here, 22 plus 20 plus 28, which is 30 plus 20 plus 20, which is 70. So I'm doing that in a weird way because I don't know, my brain works in a strange way, but I think that's 70. Okay, what about left endpoint with 5? So left endpoint, I'm now doing the under approximation since this function is increasing. And so this looks like this, and basically the first one I'm plugging in 0, so it should be 1 times 3 plus, and then it's these values except for not the last one. So 3 plus 4 plus 7 plus 12 plus 19. So that should be 14 plus 12 plus 19, which is 26 plus 19, which is 25 plus 20, which is 45. So you can see there's a huge difference between the over approximation and the under approximation. Now it says use your calculator to find the exact value. So this is going to be a new skill. We're going to go to y equals, and we're going to enter in our function, which was x squared plus 3. And we're going to graph it. Change my zoom to the zoom standard. It looks like that. And I want to find the area under the curve from 0 to 5, so I'll do second calculate. Integral, lower limit is 0, upper limit is 5. Boom, area. Incredible. So it tells me that I get 56.6 repeating. So we can see that indeed the 45 is an underestimate and the 70 is an overestimate. The trapezoidal approximation, by the way, would be the average of the right and the left. And that would be, let's see, 70 plus 40 is 110. 115 divided by 2, which is 57.5. So trapezoidal actually gives you a pretty good approximation by averaging the two there. Okay. Turning to the back here, a few more examples. So now we've got negative 6x squared plus 16. They want us to find the area between negative 4 and 4 using a right endpoint approximation with 4 subintervals. So we've got a length of 8, so we're going to have basically a width of 2. Okay, so right endpoint, we're using the right side, so that should be here, and there, and this one is actually 0. So our width is 2, and we're going to multiply by our heights. So this was negative 2, and if I plug negative 2 into my function to get that height, it should be negative 4 plus 16, which is 12. So 2 times 12 plus, plugging in 0, I get 16 for this rectangle right here. And on this rectangle, plugging in 2, I should get plus 12, and then plus 0 for my last rectangle. 1, 2, 3, 4 rectangles. And that should give me 2 times, let's see here, that's 10, 20, 30, 40. So that gives me an approximation of 80 being the area between there. Then using a left endpoint with 8 subintervals. So now I've got basically a whoopsies. I've got a rectangle every 1. Right. Left, first one's going to be 0, next one's going to be there, next one's going to be there, next one's going to be there, next one's going to be over approximation, over approximation, over approximation, and over approximation. 1, 2, 3, 4, 5, 6, 7, 8. Width of 1. Then I'm multiplying by this height, which is 0, plus this height. I'm plugging in -3, so that should be -9 plus 16, which is 7. And then I'm going to be adding 2, which was f of 2, which is 12, g of 2 rather, g of 1, which is 15. Is that right? Wait.